We were first introduced to ShengkeZeng in Los Angeles, and he talked about that very aspect. And this is what got IATR most interested in the project, to assist regulators. What we really need are some specifications to identify which camera systems are acceptable, which ones aren't, and to allow cities to bring in effective camera programs. There have been a number of distributions from ITR on behalf of Professor Zeng, helping to recruit individuals to be part of that evaluation, and we're looking forward to his comments this morning.
Thank you. Thank you. And I'm with Cami in the same division, but I'm from the protective technology branch. It is an engineering branch. I'm an engineer, so I just look at the camera in the angle of engineering. This project is also initiated by Dr. Amandas, and he's retired now. Also, I want to say any data I present here is a preliminary, considered preliminary, because they don't have a peer reviewed. So anything is not peer reviewed, we should consider as a preliminary. And a little bit of background. So Cami just described the risk of taxi cab drivers, and I just say it is speculated that the taxi cab camera might be effective, and there's no taxi cab camera selection guidelines in the U.S. and IATR just request this taxi cab camera selection criteria. Our objectives are first to develop the minimum parameter requirements for taxi cab camera system evaluation. This is the most important, just like we set the bars, and then we'll use these bars to test the sample cameras. So we'll use the minimum requirements to evaluate the 8 sample cameras. And then we'll determine the future research topics and develop the technical guidelines for the taxi cab camera selection and usage. The method to test the taxi cab cameras is the first test the reference camera to obtain the thresholds, the parameter thresholds. And the second, to use these thresholds to test 8 sample cameras. To test the reference cameras, we developed the human subject photos with various degrees of resolution degradation, exposure, underexposure, overexposure photos, and the distorted photos, lens to simulate the lens distortion, and to simulate the motion blur to determine the shutter speed, what kind of shutter speed we need to get acceptable facial photos. And then we send all these photos. We took about 13,500 photos, and then we select 4,800 photos sent to the photo evaluators to evaluate the photo quality and to vote for the thresholds. And then we'll convert the photo thresholds into the numerical thresholds. That means for resolution, we'll convert the resolution photos to the line width per picture height. And for the dynamic range, we'll use the EV, the exposure value. The people that play with the camera will know that the exposure value equals to one step, F1 step exposure. And distortion use a percentage. The shutter speed will use the shutter speed of 1/50th or 1/15th of a second. And we'll test the sample cameras. First, use the sample cameras to photograph the test chart. And then we'll convert the test chart photos into the numerical threshold, numerical parameters. And then we'll compare these numerical parameters with the threshold parameters. And then the number of a sample camera photo needed is only about 480. We'll evaluate the video recording parameters to check the necessary functionalities, to check the frame rates, storage, event triggering, and to check the security and the data privacy. Also, we'll evaluate the physical parameters of a video recorder to check whether they're waterproof, fireproof, or tamper-proof. And then we'll develop the future text cap camera research topics. The two main topics in my mind was the fire resistance test to provide the fire protective storage media chambers. And the second is the feasibility of a real-time radio frequency photo transmission from the transmission of the cap images. Now, first of all, describe the method of the reference camera test, and later we'll describe the sample camera test. So we'll use the special test charts for the resolution and the dynamic range tests. You see the test chart. There's a slanted square. This is for the resolution. We can use this slope to test the photo resolution. And there's the Kodak Q14, the grayscale step chart. And there are about 20 steps, gray steps. It will represent about 6 EVs of a dynamic range. And here it's a stripe blocks for the blurriness control. So we'll take a different resolution of the photos. So we use these blocks to control the blurriness. And this we have 10 subjects photo boards. So we'll put these photo boards to this photo chart, and to ensure for every resolution we have a face photo, and we have a corresponding resolution photo here. So whenever the evaluator votes for a certain resolution, we can use this photo chart to convert the voting into a numerical resolution. That is a line width per picture height. We'll send out these test photos to the evaluator. You see, for every subject, you have a 6 degrees of resolution, from over 1,000 line width per picture height. Picture height we define as 30 centimeters, so about one head plus some neck, and down to 48 line width. Later, we can see that the most evaluators will choose this range, 50 to 80 line per picture height. And this is the method to test to develop the dynamic range test photos. So for the dynamic range, we have two extremes. One is overexposure, one is underexposure. To get overexposed pictures, we just enlarge the camera apertures, and to make it overexposed, to make the highlight portions washed out here. This is step chart. You see, in this case, 4 blocks are merged, so you cannot see them. They are all white. And the dynamic range will go from the highest dynamic range, about a little bit over 6 EVs, down to 5 EVs. And this is the underexposed pictures. We just reduce the camera aperture. The shadow portion of the step charts will be darkened. You can see these these steps, and the reduced dynamic range is from over near 6 to 3.3 EV. EV is the exposure value. And these are the dynamic range test photos we sent to the photo evaluators. These are the overexposed photos. We call the highlight dynamic range. And here is the underexposed photos we send to the photo evaluators. We call this a shadow dynamic range photos. And then we'll produce some, develop some lens distortion photos. We cannot manipulate the cameras to obtain this distortion, so we use Photoshop to simulate the lens distortion. The distortion range is from no distortion to 15% to 75%. And this is the test photo charts for motion blur for shutter speed. So we make these subject photos onto a rotating board. We're rotating this board and use a reference camera to take the rotating pictures with different shutter speeds from 1/15th of a second to 1/50th of a second. So we take 6 steps. And first we have to determine the head shaking speed. So we have the experiment to test the common people shake their head, the speed, what is that common speed. Later I describe the test if I have time. And this is the test photo that we send to the evaluator. You see 1/50th of a second is very clear, the picture. 1/15th of a second. 1/15th of a second is blurred, very blurred. I'll show you later, most of the evaluator will choose this range. 1/30th and 1/40th. So we have 13 volunteer photo evaluators. 9 of them has core experience in facial identifications, taxi cab facial identification. 3 of them has the identification experience in the taxi cab camera industry, and 1 with experience as the taxi cab fleet manager. So this is a procedure. We send the test photo files for 4,800 test photos to the photo evaluators for the threshold vote. And then the evaluators will vote for the threshold photos in resolution, highlight dynamic range, shadow dynamic range, lens distortion, and the shutter speed. Then we use the photo test software. It's called IMATEST, 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 to convert these photo thresholds to the numeric thresholds. Oh, I mentioned I have a PDF file of these slides. So anybody, if they are interested, can email me. At the end of the presentation, I have an email address available. So the sample test, the test charts, we have a special test chart, and it's different from the reference camera test charts. First of all, the sample cameras, their resolution is not as good as a reference camera resolution. So we doubled the step chart, and here we just increase the contrast of the tilted square for the low dynamic range sample cameras. And here we have a vertical strip to test their distortion, lens distortion. Here, that's a real scene of a sample camera test. You see this vertical strip is curved. So that means there's a distortion. So the software will catch this curvature and determine what's the distortion. Here, this is also the real test scene taken by a sample camera. There's a rotating chart. We designed this rotating chart, have 6 blocks, 1, 2, 3, 4, 5, 6. And every block represents 1 shutter speed. If the camera, sample camera shutter speed is faster than this block, and then you see, actually when this rotating board is still, and what you see is a bunch of blocks, small dots. When you rotate, you see the curves here, the arc curve. If the speed is faster, you see the gap here. If the speed is slower, and then if the speed is is faster, and then you see the gap. If the speed is slower, you see these two. This block will be invaded to another block. So here we can determine this camera shutter speed is 1/30th of a second. It's just merged. These two curves merge, but there's no invasion to the next block. So this is the easier way we can determine the sample camera shutter speed. These are sample camera test procedures. First, the sample camera will photograph the test photos. Second, the software will retrieve the camera parameters from the test photos: resolution, dynamic range, distortion, and the shutter speed. Then we'll compare the sample camera parameters with the threshold parameters. And in this way, the characteristics of the sample cameras. And this is simulated taxi cab light. We use 6 LED panels and 4 incandescent lights. Incandescent light were used to simulate the sunset light condition with a lower color temperature. This is a real experiment setup. We use the retired police car as a taxi cab. And here, the arrows are gone. This is inside the cab. You can see 2 cameras. One is the infrared camera is on the top, and the bottom is a Nikon D5000 camera. And you rotate the camera. You can take a position with either the infrared camera and the regular camera. And on that corner, that is a controller for LED panels. We use LabVIEW programming to program that control to program the control program. The fire resistance test. So there's no standard for a taxi cab fire profile fire test. So Western Australia and Victoria in Australia, they have a standard. They use a NCE 119 standard. And that standard is use a furnace to heat to 1,000 degrees Fahrenheit. Then you place the recording media storage. That's a storage chamber. Inside the chamber, there's a recording media like a SD card, a CF card, a compact flash card. And you put the chamber inside the oven for 5 minutes. And after 5 minutes, you just shut down the oven and immediately take this media out. Then we'll see whether the SD card will survive this oven test. That's an electric oven, and that's the storage chamber. We use the heat insulation material to build that small chamber, and with the several thermocouples inside or outside the chamber to record the temperature. progress to date, we developed the procedures for the reference camera and the sample camera test. We measure the light intensities in a simulate taxi cab in various light conditions. We measure the 7 light conditions. Daylight condition is a very strong light, over 100,000 lux illumination. Cloud, 10,000 lux, and the heavy cloud, 1,000 lux, and dusk, so 100 lux, around that level. And the dark condition, sunset, the light via a rear window, that's a very severe light condition. And dark with a backlight. We developed the camera test equipment and set up and determine the head shaking speed, and took more than 13,000 photos, and use the color and the infrared camera. We choose 4 extreme light conditions: daylight, very strong light, sunset via rear window, that is very bad for a camera, facing to the sunset light, and dark, no light at all, and the dark with the backlit. So the dark with some headlights shining from the rear window. That's very bad for camera. We take pictures in 3 cab seats, front right, rear middle, and rear right. For another 2 seats, they are symmetrical, so we don't take another 2 seats. With the 6 resolution steps we just saw before, and the 10 dynamic range, 5 overexposed, and 5 underexposed. 6 shutter speeds. We select 4,600 photos from the other 13,000 photos, and send the photo files to the 13 photo evaluators. We get the 12 results back. We complete the analysis on the evaluators of photo evaluation results, and also we convert the results into the numerical parameters. We tested this 8 sample taxi cab cameras. Some of them are market available, and some of them are production cameras. And also we tested their video recorders. We completed the waterproof tests to test their SD cards and the CF cards, and we don't have to test the whole chamber. So if cars can survive, so we just reserve all these images, and we'll conduct the fireproof test for the recording media chambers using the NC standard E119. That's the 1,000 degree Fahrenheit in 5 minutes. And we conducted the computer temperature profile simulation using a final element software ANSYS. Preliminary result, we just say they are preliminary. And first, the reference camera, the resolution threshold converted to the numeric parameter is from 57 to 89 line widths per picture height. Picture height is, we remember, 30 centimeters. And so the range, this threshold range is comparable to the Victoria Australian standard. When you convert their standard into a 30 centimeter picture height, it is about 108 pixels. You see, this is a pixel. This is a theoretical resolution. Our resolution is a real measurement. So their pixel count is higher than our line width, but you have to consider the lens loss and the compression loss, everything considered, and the real line width must be lower than 108. So this threshold range is a challenge for the regular resolution camera. I mean regular resolution is 480 pixels, vertical pixels. It's very difficult for these cameras to keep the real seed image clear. Dynamic range. The highlight dynamic range is about 5 EVs. The shadow dynamic range is lower. The average is about 4.919. So here you'll see the human eyes, at least we say the photo evaluator's eyes, are less tolerant to the highlight, to the highlight washout pictures. So it's easier for them to detect the shadows underexposed pictures. For the distortion, it's ranged from 15% to 45%. It's diverse. So we say the human eyes are less sensitive to the image distortion in facial identification. And unfortunately, most of the sample cameras, their distortions are lower than this threshold. Shutter speed. For some lights, the shutter speed is 1/40th of a second, and for some is 1/30th of a second. So average is 1/35th of a second. And fortunately, most of the sample cameras, their shutter speeds are faster or just close to this threshold range. We use a 6 SD card and compact flash memory card put into the 5-meter high pipe full with the fresh water for 3 days, and then we'll take the cards out of the water and to let them dry, and all cards are survived. The images on the card are reserved. And for the sample cameras, every sample cameras we check, there's no fire protection. It's not a fire resistive. So we just try to think of what kind of material we can use to build these fire resistive chambers, storage chambers to resist these 1,000 degree Fahrenheit 5-minute fire profile. And the memory cards can survive this fire profile using a microtherm material. It's one thermal insulation material used to build this black box in the airplanes. And the other material we tested, it failed. This is a waterproof test. Here you can see the 5-meter high pipe, and on the bottom you see the SD cards and the CF cards merged into the in the water. And this is the temperature curve of the fireproof test. Here, there are a bunch of microtherm material tests. All of them pass this is under the threshold. This is 85 degrees C, 185 degrees Fahrenheit. That's the memory card storage temperature. They're lower the temperature. This is the 5-minute line. After 5 minutes, the cards, the storage chamber was taken out of the oven, but still you can see the heat inertial will cause the temperature go higher. But this is not a material. Their temperature is much higher than this car, so they failed here. And all this microtherm material, the card inside the microtherm material that survived. We can see the photo resolution range is from 57 to 89 line width per picture height, and it's comparable with the Victoria Australian standard, 108 pixels. And The second is the real-world resolution reductions of the regular camera. That's a 480 pixels, vertical line pixels. The quality, the resolution reduction may reduce the real resolution below our threshold determined by the evaluators. Human evaluators seems more able to identify underexposed facial images than overexposed. So lens distortion is a less important factor in the camera selection. This shutter speed range seems to be is not to be difficult for most of the sample cameras. Flash card can survive a 5 meter 70-hour fresh water test, but we don't know what happened in the salty water. The fire-resistant chamber might protect the memory cards in a 1,000 degree Fahrenheit 5-minute fire profile. Remaining tasks. The first work, we should complete the analysis on the sample camera test data. And we'll complete the test report and the selection guidelines in the summer next year. I will submit the manuscript for a peer review and submit for publication in winter 2013. This is our contact information, and please remember my email address, szeng@cdc.gov. So if anybody they want the PDF file of these slides, please email me. Thank you.
Shenke.
Yes. Thank you.
Just since we're short on time, just one brief question. When you did your evaluation, I saw that you had a cab that was a former police vehicle.
Right. Mm-hmm.
Now that's normally just a two-seater, but well, 2 rows. Now in most jurisdictions, we're going to vans and SUVs. Have you all taken in consideration vehicles with 3 rows of seats?
No, we don't have any funds for this project, so this project is done already. I'm sorry, just 2 seats, two rows.
Okay.
Mm.
Shenke, on behalf of IATR, we would like to thank you for your commitment to improving driver safety, as well as you and Cammie's commitment as far as collaborating with the IATR on this report, and we look forward to your report.
Thank you very much. Thank you.